Hello fellow OPs and welcome to another video on the OpHaxor YouTube channel. Today we're going to be going over another LeetCode problem, 1372, longest zigzag path in a binary tree. So this is a tree problem. We're going to be using a depth first search algorithm with a that is recursive. So this problem is interesting. We're going to have fun with it. Let's go ahead and get started. So let's go over the problem statement. Given a binary tree root, a zigzag path for a binary tree is defined as follows. Choose any node in the binary tree and a direction, right or left. If the current direction is right, then move to the right child of the current node. Otherwise, move to the left child. Change the direction from right to left or from left to right. There's a typo there. Repeat the second and third steps until you can't move in the tree. So the zigzag length is defined as the number of nodes visited minus 1. So that means a single node has a length of 0. And we return the longest zigzag path that is contained in a tree. So let's go over example 1. We are starting our zigzag at the second, or the one on the second level of the tree, right here. So we're starting out by going right, go right here, and then because we went right, we have to switch our direction to left, left, and then right, and that's it. That is the longest one. If we had started at the root, we would be able to go right and then left, and we would be stuck. So that's why we start here, right, left, right, and our output is 3 because so again, number of nodes visited minus 1. So 1, 2, 3, 4, minus 1 is 3. Or you can view it as just the edges, 1, 2, 3. Let's go to the second example. So for this one, we start at the root, and our first direction is left. So we go left, right, and our longest zigzag path is 4. Example 3, if you just have a root, then that's it. Your longest zigzag path is 0 because there are no other nodes that can be visited. Alright guys, so let's go over the solution. We are now in our Eclipse IDE. Let me show you what's going on here. So we have our tree node static class, which is given to us by LeetCode. We have our solution methods. This is straight from our solutions on the OpHaxor website. And we have our main method where I'm instantiating the variables. So let's go ahead and start a debug session. Alright, so now we've instantiated our tree. This is the same tree that you guys can see. It's example 2 from LeetCode. So let's jump into our method, longest zigzag. And then here we're going to just go straight into our recursive DFS method. So this is our base case. If the root is null, then we return 0. That represents 0 length. Now we have int L equals DFS node left, and then false, that's just a Boolean for whether it's a left variable. So let's see what's going on here. This method is going to give us our length call if we were starting our zigzag search at this node, right? So let's go into that. So that means right now we are on the one on the second level of the tree to the left. So it's the the left child of the root. And now we're gonna, when we call this, right, obviously this is gonna be null because the left child of the root does not have a left child itself. So it's null, we return length of 0, and we can see that L. Alright, so I made a minor modification to our overlay here. I put the tree from LeetCode into our whiteboard so we can better talk about what is going on here. So I'm going to call this one A, B, C, D, E, F, and G. Alright, so right now we're on B, and L of B returned 0 because B does not have a left child. So R, we're going to go into R, and actually I'm going to label what just happened on the whiteboard. So L of B is 0, and now we're on right of B, so now our current node is D. And when we go into L, now we are on node E, and if we go into that, we're going to return null because E does not have a left child, so that's 0. And when we go into the right node, now we're on node G. So L and R are both going to return 0 here. And we can see that 0, 0. Alright, now let's see what happens when we go past these two. So remember, we're on G currently. So we do math.max of the current result. So result here, we have our, it's a field. So the whole class can see it, and it is it's a constant value, or not a constant value, but every recursive call can see the same value for result. So we just math.max it with what we got here. So result is 0, L and R are both 0, so result ends up not changing. And then we return our sum for the parent. So is left. If it's a left, if this is a left node, then we return 1 plus the value that we got for L. So for G, since the isLeft boolean is true, and essentially what this boolean is it doesn't actually represent whether it's a left node. What it really represents is the alternation. So this value is always going to alternate. So when we first call the DFS function, we pass true, and then when we go left, it becomes false, and then when we go right, it becomes true. So it's an alternation, is what it is. So G returns 1 because L and R were both 0, so 1 plus 0. And now we're back at E. So E has an L value of 0 and an R value of 1. So let's record that. Zero, R, 1. And of course, right? So we math.max L, that's still going to be 0. We math.max result, and that is going to be 1. So you can see result has turned into 1. And now here, the isLeft variable is false, so we're going to record the value from R, so we do 1 plus R. So we return 2 for that parent. Right, so now we're on D. So D got an L value of 2. And I'm not going to go into the R value DFS because we get the idea. So F is going to return 0, or L is going to have 0 for L and 0 for the right node as well. So that means it's going to return 1 to D. So D will have an R value of 1. If I run that, we can see 1. So again, we math.max results. Result will turn into 2 because L is 2. That will not do anything. And then again, the isLeft is now true because we're alternating. So return 1 plus the L value. So L value is 2. We return 1 plus 3 to the parent, which is B. So that was right. That was the right child of B. So let's record that. We got 3. And yep, 3. Math.max L, that's 0, will do nothing. Math.max R and result, so we have 3 as the new value. Result will become 3. And isLeft is false, so we're going to get 1 plus the value for L. Which means we will be returning isLeft is false here, so we will be returning the value for R. So we will be returning 1 plus 3 to the parent, which is A, the root. So A has an L of 4, and we know that this is going to be 0, which means R will be 1 for A. And indeed it is. Math.max the results, so result would turn into 4 because L was 4, and we don't care about the return value here, and we simply return the result. That's it, 4. And there is indeed 4 zigzags in this tree. So this problem showcases the beauty of recursion. It's very useful for tree problems. We are doing a depth first search because you can see when we go past the recursion, or when we first start calculating results, we are at G. So the node with the highest depth on the left hand side. So this has the highest depth out of everything. That's G. And then the next value we calculate is E, and so forth. And of course F and then D. Right. So I hope you guys enjoyed doing this problem. Leave a comment if you have any questions or if you would like to provide some feedback. Otherwise, please like and subscribe, and we'll see you next time. Thank you very much.